Introduction. There had been a long-felt need for a compact busbar system for medium and high-voltage power interconnection in outdoor switchyards and switchgear rooms. Medium-voltage bus ducts have unwieldy dimensions for a rating of 24 kV and above. When installed indoors, it occupies a disproportionately large volume of the room. When installed outdoors, it requires an expensive supporting arrangement. The typical cross-section dimension of a 36 kV, 2,500 amperes, air-insulated, segregated phase bus is 2,400 mm, 108 inches, in width and 800 mm, 32 inches, height. Air-insulated circuit breaker panels are cost-effective for voltage rating up to 36 kV. To make the panel compact, the conductors are either sleeved or cast in resin to share the insulation stress. Interfacing a bus duct with the panel is challenging. Gas-insulated bus is expensive for medium-voltage applications unless it forms part of the gas-insulated switchgear. The arm of the gas-insulated switchgear can be extended for connection to the transformer or neighboring switchgear. Sulfur hexafluoride gas has been identified to contribute to the greenhouse gas effect. In contrast, solid insulated bus bars are compact and need less installation space and time. Solid insulated bus are manufactured up to a voltage rating of 170 kV. Single-core XLPE cable, one cable per phase, has been included in this category as it can very well be installed for medium, high and extra high voltage interconnections right up to 500 kV. After establishing their viability for a project, they can be considered as an alternative to the bus ducts up to 36 kV and gas-insulated bus beyond 36 kV. XLPE cables are manufactured in continuous lengths and wound on drums. It may not be easy to procure small cut lengths to meet the requirements of short connections. Organic insulation materials age with time. The cross-linking bonds become weak and break. This happens even under normal operating conditions. When they are subjected to thermal and dielectric stress higher than the rated value, the aging process accelerates. It is believed that an increase in the operating temperature by 8 to 10 degrees Celsius reduces the service life by half. An increase in the operating voltage by 8 to 10% reduces the service life by half. Insulation subjected to thermal surge, due to overload and short circuit, and repetitive voltage surge, due to lightning and switching surges, can seriously impact the life of insulation. Description. There are several categories of single-phase, solid insulated busbar system that can be used for a wide range of system voltage. These are classified based on the insulating material of the conductor. XLPE insulated, resin encapsulated, resin impregnated paper insulated. These are ideally suited for making connections between transformers located in outdoor switchyards and indoor panels, between indoor panels and between equipment in switchyards. The judicious selection of solid insulated bus makes the switchyard interconnections compact. When an existing switchyard needs to be upgraded to receive an additional line or installation of a new transformer within a constrained area, it may not be possible to install bare conductors with recommended clearances to undertake the modifications. Solid insulated bus can offer a viable solution. All solid insulation buses have circular cross-sections and therefore can be negotiated in 3 dimensions. Since the conductor is also circular, the ends of the conductors can be fitted with terminals that can be oriented in any direction to interface with the equipment terminals. XLPE cable bus. Single-core XLPE cables are manufactured for a rating, up to 500 kV, and are in operation for the past few decades. While its application is most common for long-distance power transmission for high-voltage and extra-high-voltage systems and various interconnections between equipment, transformers, switchgear and motors, in the medium-voltage system, it can be very effectively used as an alternative to a bus duct under certain ampacity constraints. Not only will such alternatives be more compact and space-saving, but they would also be more economical. XLPE cables are manufactured with copper or aluminium conductors. Single-core XLPE cables with copper conductors are manufactured up to 2,500 mm², 5000, with an approximate ampacity of 2,500 amperes in air and 2,000 amperes when buried or run in trenches. XLPE cable connections require clamps and terminating accessories. These are specific to the cable's size, rating, and construction of the cable. Terminating accessories will also depend upon the terminal arrangement of the connected equipment and its location, indoor, outdoor. Terminations are carried out on exposed outdoor bushings, inside cable end box, panel, or interface with a gas-insulated switchgear. Clamps can be designed for either holding the cable firm or allowing it to slide along the axis. Fixed and sliding locations are designated based on the routing. Customized support structure facilitates ease of clamping to cater to the site tolerances and running an earth bus. Terminating kits are manufactured to international standards for a wide range of connections. Resin encapsulated bus. Resin encapsulated bus are designed to be installed in a system with a rated voltage up to 36 kV. They are ideally suited for indoor installations in switchgear rooms and outdoor installation in switchyards, interconnecting transformers and panels. A tubular conductor is pre-formed and encapsulated in resin along its entire length for the desired insulation level. The resin encapsulation process is carried under vacuum and cured to remove any remnant stresses. A corrugated polyamide outer sheath of adequate thickness covers the entire length of the cast conductor for protection against moisture, ultraviolet radiation, and direct rain. The insulation also protects the conductor from experiencing a fault caused by accidental bridging of phases or phase and earth by birds and rodents in outdoor switchyards. Resin encapsulated bus are manufactured up to a length of 10 meters, 33 feet 4 inches, and a rating of 3,150 amperes with aluminium and 4,000 amperes with copper tubular conductors. The degree of protection provided for the conductor is IP67. The conductors are joined at the site with aluminium or copper laminates of compatible current rating with a cylindrical enclosure sleeve that offers a minimum degree of protection of IP54 for indoor and IP68 for outdoor installation. The laminated conductors cater to the linear expansion/contraction of the conductor due to temperature variation based on the insulation level of the encapsulated conductor. They can be classified as fully insulated bus, partially insulated bus, resin encapsulated, fully insulated bus. The conductor is encapsulated suitable for a voltage of 3.6 kV and a basic insulation level of resin encapsulated, partially insulated bus. A conductor is encapsulated to withstand a voltage of 7.2 kV with a 1-minute power frequency withstand voltage of 28 kV. These conductors, though insulated for 7.2 kV system voltage, can be used for a system voltage up to 36 kV by mounting them on an appropriately rated insulator. Since the clearances to other phase conductors and earth are significantly reduced due to the conductor insulation, the entire assembly of a three-phase connection becomes compact. Table 12.1 details typical phase spacing and height of the insulators for different voltages. Rated voltage, basic insulation level, minimum height of the insulators, phase-to-phase and phase-to-earth clearances. For rated voltages varying from 12 kV to 36 kV. Resin-impregnated paper insulated bus. Oil-impregnated paper wound conductors have found application in high-voltage cables, instrument transformers, and bushings since the end of the 19th century. Over the years, with the increase in the transmission voltage and the development of appropriately rated cables and condenser bushings for the transformers, their thermal and dielectric properties have been well researched, recorded, and documented. Impregnation of paper with oil is a comparatively risk-free process. Oil does not undergo a chemical transformation. If there be a minor deficiency in the dielectric properties of the finished product, it can be made good by reprocessing. Cast resin insulators, bushings, and instrument transformers for medium voltage applications have been in operation for many decades. The casting process of the components is well understood. However, when the paper is impregnated with resin, as in the case of a solid insulated bus, the resin undergoes a chemical transformation. The entrapment of moisture or air will adversely affect the dielectric properties of the product. Reprocessing cannot be carried out to rectify defects. The process of impregnating paper with resin was developed by Moser Glaser in the late 1950s. The process was subsequently adopted, modified, and improved with the development of new resin formulations. The solid insulated bus comprises four major sub-assemblies. Insulated conductor with bends, site joints assembly, end termination, support system, insulated conductor with bends. A solid insulated bus connection is designed to have the least number of site joint assembly. The insulated conductors are made as long as is permitted by constraints of transport and installation. Bends are an integral part of the insulated conductor. The maximum length of the single conductor with length depends upon the rigidity of the conductor. The larger the diameter of the conductor, the longer can be the individual length of the conductor. Conductors can be manufactured with a straight length of up to 13 meters, 43 feet 4 inches, with 1 or 2 right-angle bend totaling 3 meters, 10 feet. Sight joint assembly. Sight joint assembly is the most critical subassembly. Its design differs for indoor and outdoor installation. For indoor installation, the minimum degree of protection is IP55, while for outdoor it is IP68. Further, the outdoor enclosure must withstand the effect of ultraviolet radiation, rain, snow, and erosion due to high wind velocity with dust particles. The sight joint assemblies are ampacity and voltage specific. The sight joints are made with laminates to cater to the expansion and contractor of the conductor due to temperature variation and minor misalignment in the axial direction during installation. The cross-section of the laminate will depend upon the ampacity. The length of the sight joint assembly depends upon the voltage. Since the joint is made in the air, adequate creepage distance needs to be provided. The sight joint cover should extend beyond the earth ring on the insulated conductor to limit the field strength. The inner surface of the sight joint enclosure has a conducting shield which is kept at the same potential as that of the conductor by a spring-loaded conductor. The outer surface of the sight joint enclosure has a conducting shield which is connected to the earth. This arrangement ensures that there is no discharge from the live conductor and the enclosure is touch safe. End termination. End terminations are specific to the location, indoor or outdoor, and connected equipment. Outdoor connection to switchyard equipment, medium voltage and high voltage. Transmission line, medium voltage and high voltage. Transformer bushing, medium voltage and high voltage. Transformer cable box, medium voltage. Indoor connection to switchgear panel, medium voltage. Gas-insulated switchgear, medium voltage and high voltage. Manufacturers have standard designs for end terminations with adapter box for different current and voltage ratings that are customized to suit the connecting equipment. Support system. These are customized supporting arrangements for indoor and outdoor installations. Fixed and sliding support blocks are manufactured to suit the product. Table 12.2 details the specification of solid insulated bus comprising rated voltage, kilovolts. 1-minute power frequency withstand voltage, kilovolts. Impulse withstand voltage, kilovolts peak. Rated current, amperes. Conductor material, conductor shape. Outer sheath material for straight run. Outer sheath material for bends. Conducting shield material. Weight. Bending radius. Maximum total conductor length. Thank you. Mr. Balachandran graduated with a bachelor's degree, B.Tech, in electrical engineering from the Indian Institute of Technology, Madras, India, in 1967, and obtained a master's degree, M.E., in power engineering from the Indian Institute of Science, Bangalore, India, in 1970. He is a Fellow of the Institution of Engineers, FIE-India, Fellow of Institution of Engineering Technology and Chartered Engineer, FIET-UK, and Life Senior Member of the Institution of Electrical and Electronics Engineers, IEEE-US. He was the Founder-Director of Power Gear Limited and Busbar Systems, India, Limited. He has worked in manufacturing industries in India and the UK and is currently an advisor. He has engineered several busbar systems that have been manufactured and installed in various countries, including isolated phase bus for the largest hydroelectric power plant, 26 by 800 megawatts, at the Three Gorges project in China. During his professional career, he has developed and tested a range of bus products and their accessories. His area of interest also includes switchgear, instrument transformers, and power system analysis. The book, An Introduction to Busbar Systems, authored by V. Balachandran, is case-bound, hardcover, size A4, 386 pages, printed on 100 GSM glossy paper. Copies of the book can be purchased with a requisition to Bala at busbarsystems.net. Black and white version of the book is for sale in India, Afghanistan, Bangladesh, Bhutan, Nepal, Pakistan, and Sri Lanka at a cost of 4,500 Indian rupees plus freight. Color version of the book is for sale in all other countries at a cost of US $126.00 plus freight.